So two small speakers right here are positioned a distance of 0.75 meters from each other, and those speakers are emitting a 2500 hertz tone. The sound waves from the speakers are in phase with each other, and then you have a student standing over here at point P, which is 5 meters from the midpoint of the speakers, and we're going to use 343 meters per second for the speed of sound. So for part A, we just want to calculate the wavelength of the sound waves. And we know the equation, V is equal to lambda F. We've been using a C in a lot of these problems because we were dealing with the speed of light, but now we're dealing with the speed of sound. So we're going to go back to using the V. So lambda, the wavelength, is equal to V over F, which is 343 divided by 2500 hertz, and that gives you a wavelength of 0.1372 meters. For part B, the student moves a distance y, so that's down here, to this point Q, and notices that the sound intensity has decreased to a minimum, and it wants you to calculate the shortest distance the student could have moved. So this is where we see that this problem is kind of like the sound equivalent of the double slit diffraction problem, because instead of light passing through two slits, each with the same wavelength, we have sound coming from two speakers that are a certain distance apart. So we're going to be using the same equations that we were using for the light diffraction. So we'll look at, to find this distance y, that is the equivalent of the xm that we've been solving for. And in this case, this is the first place where he gets to the minimum. So we want to use the approximation xm is approximately equal to m lambda L over D. Now for the double slits, the m is an integer when you get to the bright spots. That's where you have constructive interference, which means that m would be a half integer, like 0.5 or 1.5, when you get to the dark spots, or the destructive interference. In this case, since we're talking about the sound waves kind of canceling each other out and giving you a minimum, that's the equivalent of a dark spot, which for this would be a half integer. So the smallest distance he could possibly go from this point to this point would be when m is equal to 0.5. So we'll put in the 0.5 times the wavelength, which was solved for as the 0.1372, times the L, which is the distance, that is 5, all of that divided by D, that's the distance between the speakers, which was the 0.75. When you plug all this in, you get an answer of 0.46 meters. So it tells you that the student could have walked a distance of 0.46 meters to hear the minimum. For part C, identify another location on the line that passes through this line containing P and Q where the student could stand to observe another minimum. Well, the most obvious place to do this is, since it is symmetrical, if you go a distance of 0.46 meters beneath point P, you could also go 0.46 meters above point P. So that's the obvious answer to say, 0.46 meters above P, because of the symmetrical nature of the problem. So because it's symmetric. Another thing you could have done is you could actually go back to this previous thing, and instead of using a 0.5 right here, you could have just said xm is approximately equal to, and plugged in another half integer value. So for example, 1.5 times, and then everything else is the same. For part D, how would the answer to part B change? So we got the answer of the 0.46 meters. How would that answer change if the two speakers were moved closer together? So in other words, the D, which is the distance between the two speakers, is decreasing. Well, if you go and look at this equation, if you lower the d, since that's in the denominator, the xm is going to increase. So the xm increases, which means that the person would have to walk a further distance before they hear the minimum. The second part of part B says that this time the frequency emitted by the two speakers is increased. So we're saying that the F goes up based on the equation up here. If the F goes up, since the speed stays the same, the speed is constant, if the F is going up, the lambda has to go down. And you can see that right here because they're inversely related to each other. So the F goes up, meaning the wavelength goes down. And now if you look at this equation, you can see that as the wavelength goes down, that's directly related to the xm. So the xm would decrease, which means the student would not have to walk as far in order to hear the minimum.